Good morning, students. Today we will be discussing about the bonding and the structure which is present in the alkyne complexes of the transition metals, right? Earlier we had discussed about the preparations of alkyne and we had seen or observed that the basic method of preparation is by the replacement of the carbon monoxide ligand by the alkyne ligand. So when the alkyne ligand can be very easily replaced by the carbonyl ligands, carbonyl ligands can be replaced by the alkyne and we get the alkyne metal complexes. Now what will be the bond between the two, or what will be the bond in these complexes? So the alkynes with two pi bonds, you all know that C triple bond C when it is present, and we had earlier discussed the structure of alkyne, that is C triple bond C. When C triple bond C is present, we have got a single bond, that is sigma bond, and we have two pi bonds which are perpendicular to each other. So these two pi bonds which are present perpendicular to each other, in terms of molecular orbital theory, we find that these two pi bonds, they have got two bonding orbitals and two anti-bonding orbitals. So those pi bonding orbitals, how many pi bonding orbitals? 2. And how many anti-bonding orbitals? 2 anti-bonding orbitals are present in case of the alkynes. So this alkyne with two bonds, pi bonds, they can react with the metal utilizing either one of the pi bond or by both sets of the pi electron pairs. So the bonding between the alkyne and the metal becomes quite interesting. Now, out of the number of the structural type, the two extreme cases, now why we are saying it to be extreme? Because the structure lies somewhere between the two structures. So this is one extreme and this is the second extreme. The first extreme is what? This L and M, that is, this is the ligand, number of ligand is N in this complex. This is the metal and it is bonding the C triple bond C. It is approaching and it is bonding C triple bond C in this way. And the second is what happens is this metal atom, it bonds with the C and C. Both the carbon atoms, that is neta 2 type of complexes, are formed in this case of the molecules. So this is neta 2 type of complex which is formed. This is called as neta 2 alkyne complexes. And evidence for formation of this type of complexes, that is B type of complexes, can be obtained through IR, infrared spectroscopy, or proton spectroscopy, or C13 NMR. So in this, through these methods, spectroscopic methods, we have got evidences that this metal atom binds neta 2 alkyne molecule. When it binds neta 2 type of alkyne molecule, the triple bond is converted into the double bond. So now what will be the resultant of this? That we will be discussing later also. But in this figure we find that the C triple bond C is enlarged. The C triple bond C which was present here, your bond length is enlarged, and there is a change in the stretching frequency of this acetylene molecule as compared to the free acetylene molecule. So this is neta 2 type of alkene. And now apart from this neta 2 type of alkene, the bonding in these complexes can be very easily explained by Dewar, Chat and Dukanson model. But there is a structural evidence that rehybridization occurs to form relatively strong sigma bonds. What do you mean by the sigma bonds here? That means what happens is we get a polynuclear molecule. Just like in these sorts of complexes you see here LNM and LNM. That means ligands are present with the metal. Now what happens when it reacts with the acetylene? This bond, metal and metal bond is already which is existing. It reacts with the carbon acetylene and the triple bond between the carbon and carbon is broken, and both the carbon atoms are connected to both metal atoms, right? Suppose if I number this carbon as carbon 1, now you find that this carbon 1 is bonded to this metal also and this metal also, and this carbon is bonded to this metal and this metal, both the carbon atoms. Each carbon atom is bonded to both metal atoms and they are bonded to each other also. So this sort of complexes are formed, and these sorts of complexes are also formed where there is a strong sigma bond. Now, apart from neta 2 type of complexes, just earlier we had discussed about the neta 2 type of complexes. The alkyne molecule is able to form sigma bond on that alkyl derivatives also. Why? That means what happens is the metal is connected to only one of the carbon atom, that is neta 1. We are saying here as neta 1, alkynyl transition. Now when we are adding this nyl, that means it is a radical. It is not any molecule or anything. No, sorry, it is not an ion or any this thing, but it is a radical. Now what happens in this case? Alkylide. This is a radical C, RC triple bond C minus. This is isoelectronic, or it has got the same number of electrons as in case of the isocyanides and carbon monoxide ligand. So just like carbon monoxide ligands can also form sigma bond. This is the sigma bond between carbon and metal atom. So in the same way, just like this molecule or carbon monoxide molecule can form a sigma bond on a single bond with the metal atom, these alkyl radicals or these radicals can also form the sigma bond, and this, when it forms the sigma bond, that means it is neta 1. Now this complex you cannot call as neta 2 type of complex. This is the neta 1 type of complex. Now in this complex what happens is the carbon ligand is bonded with the metal C simple, and these pi bonds overlap among themselves to form the M and C bond on in this molecule. So this is the simplest method or simplest this thing which we can discuss over here. In the formation of the sigma bond, when we say that the metal and carbon is forming a sigma bond among themselves, then what happens? The C double bond C. Now when it is going to form a sigma bond with the metal, the C triple bond C bond, the bond length increases and this bond becomes weaker. When this bond becomes weaker, I had just earlier explained that the frequency, stretching frequency of absorption is lowered to 150 per centimeter in the metal acetylide complexes where negative ion is present over there as compared to that of the free acetylene molecule, right? Now regarding the nature of neta 2 type of alkyne complexes, according to the diagram, what we find is that just earlier I had explained that we have got 2 pi bonding orbitals and 2 pi anti-bonding orbitals. Among the bonding orbitals, one of the pi and pi dot orbitals of which one lies in the metal CC plane. And that means because both the pi orbitals are perpendicular to each other. So one of this bonding orbital, it lies in metal and CC plane, and so it overlaps with this to form a sigma bond. The other is perpendicular to this one, so we write pi perpendicular and pi dot perpendicular. This later pair also has got symmetry characteristics to form the bond with the transition metal d orbitals. So this is the method by which both of these can form the sigma as well as pi bond. That means the alkyne complexes, they are able to function as pi acceptor because they have got vacant pi orbitals, that is antibonding orbitals, and they can also act as pi donor because they can they can share or they can overlap their pi orbitals with the metal orbitals. Why? Because the symmetry, they have got an appropriate symmetry for the overlapping. But what the question arises here is that whether this alkyne molecule will act as a 2 electron donor or 4 electron donor. So as we all know that whenever the metal complexes are formed with the ligands, they generally obey the 18 electron or EAN rule, which was given by the Sidgwick. So 18 electron or the EAN rule is obeyed. Through that, or with the help of that 18 electron rule, we can find out whether the ligand is 2 electron donor or 4 electron donor. For example, in case of the complexes PTCH triple bond CH hold twice, or MoS2 CnR2 CO CH triple bond CH, when you calculate the number of electrons, total number of electrons by this ligand and the metal ligand, just in case of Sidgwick or 18 electron rules, then we find that this acetylene and this acetylene molecule acts as 4 electron donor ligand. So with the help of 18 electron rule, we can find out whether this acetylene molecules which are attached to the metal atom, they act as 2 electron or 4 electron donors. So basically the structure of these molecules are or the bonding or the structural functioning etc. in these molecules are very similar to that of the carbon monoxide and metal complexes, or that of the other ligand and metal complexes, where they can act as the sigma donor and the pi acceptor. That is, they can form both sigma and pi bond, that is synergic bonding can be formed in this. These are some of the examples where they act as different type of ligands. Acetylene acts, or alkyne molecule acts as a different type of ligands. For example, in this case, it is neta 2 type C. Simple, this is the metal and this is C double bond C. Actually, it is C triple bond C. The triple bond is converted into double bond, and simple neta 2 type of complexes are formed over here. This is the second example where we are having bridging. CO2 CO, that is that example which we had earlier discussed. CO2 CO whole 4 gets converted into CO2 and CO whole 6, and this acetylene molecule is added, which is having, in which each carbon atom is bonded to the metal atom, right? And this is simpler, that is a simple complex, still complex molecule in which there are 3 iron atoms, and each carbon atom is attached to all the 3 iron atoms, like this way. So this is little more complex type of molecule which is formed through the acetylene or alkyne in molecule ligand with the transition metal complexes.